I've started recording already. Seeing we're a few people short today. Um, let's wait for one more minute. Let me get most of us here. And while we're waiting, a quick announcement. Finish all the grading on the exam already. If you have any questions, please email me and we can discuss if you have any question about the grading. Okay. And homework, I'm really working hard on it. I should be finished it in a day or two. So like I said, early next week, Monday, you should have a update on the overall grade for the semester so far. Okay. Any question before I start today's lecture? Anything? Anything? Okay. If not, we will release the new homework today, and which will be due next week again, next Thursday. And this homework is going to be on the service, which is tracking, and also on the deflection, which we'll be covering today. Okay. All right. Well, I'm trying to make this lecture today short because it's really just an example. All right. So first of all, a quick review what we have learned last time. We said there are different stages when the beam undergo bending, right, moment. In terms of the beginning stage, elastic, and then goes on to a little bit of transition plateau, and then go to the second stage two, which is the cracked elastic, right? So the two stages we discuss how we compute the IGT and ICR, and we're going to use them to calculate the deflections, right? So in terms of the deflection calculations, we show that in terms of simply supported beam under distributed load, the equation for deflection is known. Most important thing for us is to find the effective Young's modulus and moment of inertia. And truth be told that because the moment distribution is not uniform, it's not a constant moment throughout, right? So that requires us to compute the effective moment of inertia, I effective. And how does this I effective compute it, right? So we have find out that the moment distribution follows a parabolic with respect to a distributed loading, and the effective moment inertia can be calculated using the equation shown here in red, and this is from ACI code. All right, so we're going to use that to calculate the moment inertia. And one thing is that from the equation, you see the parameter here is MCR and MA. MCR is the cracking moment, okay? And you can compute the cracking moment using this equation here. And the symbol here, FR, is the modulus of rupture, IGT is the gross moment of inertia, and YT is distance from the neutral axis to the tensile fiber, okay, to the optimal tensile fiber. All right, so that is how we compute the effective moment inertia. Then we talk about continuously supported conditions. All right, now when we have that, one thing I want you to pay attention is that when we have the continuous support, we have both the positive bending moment and the negative bending moment. So apparently, the section is a little bit different when we talk about positive or negative bending moment. For the positive, you can see that in the middle span, we have the compression at the top and the bars at the bottom take care of the tension. For the end support, the negative moment scenario, the compression is at the bottom and the tension is at the top. So they're quite different. They're quite different. All right. Now, because we have such a moment distribution to compute the effective moment of inertia, to compute the effective moment of inertia, we got to use this equation here. And this equation is taking into consideration the different distribution of the moment within the beam. So we have IE middle span, which means we need to find the effective moment inertia at the middle span. And we also have IE1, IE2, which correspondingly are the moment of inertias at both ends for the beam. All right, so this IE middle span is easy to compute. We have MCR, MA, where MA is applied moment at the middle span, and we have all these symbols, right? So IE1, IE2 is the same equation, but you apply different numbers. For instance, if you have a negative bending moment here, for IE1, MCR stays a constant, maybe because the section which I will show, but MA changes as well, Okay, so is the case with IE2. All right. So a quick review of the concept here, but that only gets us so far, right? So today we'd like to take a look at one example, typical example of how to calculate the deflections, all right, for a continuous supported beam. So today we're going to find the I effective, right? Effective moment inertia for the continuous, oops, sorry, they supported, continuously supported beam below, All right. So which case, right? Which case? So first of all, I'm going to draw a side view, All right. So I have a column looks like this, okay, and the beam extending like that, and this is the column again. This is the beam, and column, and column, and beam, okay, extending like that. So that's the side view. And not only that, but also I tell you the reinforcement, okay, the reinforcement. So I will have reinforcement here at the top, here at top, okay, and reinforcement here at top as well, all right? And I have reinforcement at the bottom in the middle span, okay? Now the reason why I have such configuration is at the support, I have negative bending moment, okay, negative bending moment. So that allows me to put a bar at the top to resist the tensile forces. And for this, I provided 4 number 9 and 1 number 11. Okay, so 5 bars in total. All right, same thing here, 4 number 9 and 1 number 11 bar. All right, so that is the reinforcement strategy for ends. Now in the middle span here, I provided 2 number 9 plus 2 number 8. Okay, so that is in the middle span. Now the clear span length here is 25 feet. The clear span length here is 25 feet. All right, so this is the cross-section detail. All right, and now if I draw a cut, and I want to take a look at the middle span, what I see here, let me call this AA, indicating a cut, right? What I see here is actually what? Is actually a section, let me just draw here, a T-beam. All right, this is very important. This is a T-beam. Okay, and for this T-beam cross section, so this is a all right, for this T-beam cross section, I have 2 number 9 and 2 number 8. So top layer 2 number 8, bottom layer 2 number 9. All right, and dimension wise, this T-beam has a width of 75 inches, and the flange has a 5-inch height, and the neutral axis, might as well just tell you that without you go through the hoop, we already calculated out for you, and this is 7.66 inches. Okay, 7.66 inches. And I want you to put a label here because this is at the middle span, so this is positive bending moment. Now, why this is so important? Because if it's positive bending moment, I'm pretty sure that the compressive zone is at the top, and we can compute the IGT and ICR correspondingly. Okay, IGT and ICR correspondingly. Now at the ends here, okay, at end here, since they're both negative bending moment, okay, so if they're both negative bending moment, let me just move this on the left so you can see it better. Okay, now on the ends here, although they look like this, although they look the same configuration, all right, but be careful, all right, be careful. The reinforcement now is on the top. And what are the reinforcement? There are 4 number 9s, okay, 4 number 9s, and 1 number 11. Okay, so this is section BB/CC. Okay, and if I want to write it, this is actually sustaining negative bending moment. All right, so one thing you can immediately tell, that is the IGT and ICR, well, actually IGT is some here, is the same for AA and BB. Okay, why is that? Because it doesn't matter if I do a positive or negative bending moment. The neutral axis stays the same. Neutral axis stay the same because it doesn't matter where you want to take your references. It's always the same neutral axis. Okay, the only difference here would be the cracking moment. Okay, the cracking moment. So cracking moment, which is positive, is different from the negative cracking moment at section BB. Now, why is that? Why the cracking moment is different? It's because you think of it, right? I'm just making a line drawing here. You don't really have to draw it, but just follow the thought process here. If it's positive bending moment, we know most likely the compressive zone is going to be top. Okay, I'm making our life easier, just assuming it's going to be within the flange, and the rest of the concrete are gone, right? The rest of the concrete are gone for ICR, isn't it? And for this negative bending moment, the compressor zone is actually going to be here, right? And this is actually compressive zone. And the top portion of the concrete will be gone, okay? So in terms of computing ICR, the cracking moment, you notice immediately that AA, which is the middle span, so if I call it ICR positive, okay, and ICR negative, which is for BB at ends, they're not the same. They're not the same. All right. So you should know that at the get-go. Okay. Should know that at the get-go. All right. Now, having that in mind, this is already we know, right? This is what we already know. We started doing the moment of inertia I effective, right? We start doing the moment of inertia I effective. Okay. So to solve the problem, let's take a look at the positive bending moment first. Okay. Positive bending moment section. And this is on AA. And apologize, I forgot to draw the moment diagram. So if I want to do the IE, I also need to know the MA, which is applied moment at different sections, okay? So if I use my space here, and you can just draw it in your notes following in the next page, but to save space, I'm just gonna draw it here. In my case, so this is the column center line here, column center line here, and the solid line here in the middle is the beam. So I already know the moment distribution will look like this. Okay, moment distribution will look like this. And let me give some numbers, right? I will have an MA positive in the middle span is, oh, sorry, is a positive 162 kip foot. And MA at the negative at the support is equal to a negative 225 kip foot both. Okay, 225 kip foot both. Okay, so realizing that apply moment are different at middle span, different in the middle span. So this is AA. So this is BB, and this is CC. Okay, so they're different. All right, so this is my moment diagram. Moment diagram. Okay. All right. So with that, we have all the information from the problem, and we're trying to find out the effective moment of inertia. All right. So for the positive moment section AA here, okay. So I want to redraw the section so you can see it, right? So I want to have the IGT first, right? So IGT. So I look at this section here, and let me zoom in. And I know that the height was the neutral axis. Well, by the way, I keep forgetting things. Sorry, this afternoon is a little bit hazy for me. So this is 14 inches for the web. Okay, 14 inches for the web. All right, and then let's add more detail to the section, okay? And these are given from the problem. These are given from the problem, okay? So 75 inch of width, 5 inch of a flange height, okay? And the neutral axis is sitting right here. Neutral axis is sitting right here. And I know the distance between the top fiber and neutral axis is 7.66 inches, all right? And I know also the depth, actually the depth or the height of the section right here is 24.5 inch, 24.5 inch. And the width of the web here is 14 inches, 14 inches, okay? So these are the dimensions, right? And I want to find IGT. I want to find IGT. So how do I find IGT? Okay, so naturally, if I know the neutral axis, I can divide my section into two parts, right? So if I call it part one, which is just the flange, and part two, which is the web, then I can find out the IGT. All right. So without going through the details, because we have talked about this, I can tell you the number right now. So IGT from the positive bending moment, and I calculate using the section shown here, is about 33160 inch to the power of 4. Inch to the power of 4. And pay attention, keep using this positive sign here, meaning this is at the middle span for positive moment. For positive moment, very important, okay? Very important. It is positive moment. Okay. All right. So right now, keep in mind here, this is AA in positive moment. Okay. So let's keep going, right? I'm trying to find out the cracking. I'm trying to find out cracking. So using the same diagram, right? Using the same diagram, let me just copy it. So I'm a little bit lazy here. Copy this and paste here. And that is my positive section. And I want to show, I want to solve for my cracking. Okay, and again, I'm using the positive sign here. To find out cracking, right? First of all, I don't need the neutral axis here anymore because it's cracking, neutral axis naturally shifted, has changed. Okay, so it's no longer the 7.66 inch. Instead, right? Instead, I find myself again, let me remove this 1 and 2, find myself that the compressive zone, okay, the compressive zone here should stay within the flange. All right, so how do I know that? Because I can compute KD. I can compute KD equal to a 3.73 inches. 3.73 inches. And I check that, I realize that that is smaller than 5 inch. I realize that that is smaller than 5 inch. Okay, and now don't forget, if I want to do the ICR, okay, if I want to do the ICR, I need to do the converted area of steel here, converted area steel here, and this is NAS. NAS. And if I forgot, let me tell you that the depth of this whole thing here, the depth of this thing here, D, equal to a 22 inches. 22 inches. Okay. Now, if you're looking at this, you may ask a question, when I calculate IGT, do I need to convert the area? Yes, you do. Yes, you do. So I forgot to mention that you also need to convert the reinforcement into concrete here by this strip. And this little wing here, N minus 1 AS. And again, the depth here, let me provide that information, is 22 inches. Okay, 22 inches. All right. But for this cracked moment inertia, this is what I end up with. Okay, this is what I end up with. And sorry, let me obtain this value here. I can directly calculate this value here, ICR plus, okay? Make sure you know this. This is positive only, okay? And that is 10860 to the inch of power of 4, to the inch of power of 4. Okay, so I already gave you this. Okay, all right, so this is the positive section. I have my IGT, which is this number here, have my ICR, which is this number here. Of course, I skipped tons of details, okay? I skipped tons of details, but you should be able to follow the process we talked about last lecture to get this, okay? To get this, all right? So that is for the positive section, So section number 2, what about a negative section? So BB or negative bend moment, negative bending moment. Okay, so how do I do that? First of all, I know that IGT negative equal to IGT positive. All right, so I don't have to compute IGT. Okay, so IGT equal to what? We already computed it out. So 33 number here is 33160 inch to the power of 4. Okay, that is the first stage, right? First stage. And now ICR negative, we know that this one does not equal to the ICR positive, does not equal to the ICR positive. All right. So if it doesn't, what is it? What is it? How do we compute that? How do we compute that? Okay, let me give you some hint, right? So I look at a section here, and again, let me redraw it, okay? Look at the section here, it's a T-beam. Okay, it's a T-beam. And here I have my reinforcement, right? I have my reinforcement. So I convert my reinforcement here, and this is 4 number 9 plus 1 number 11, right? And I convert that multiplied by n. Convert that multiplied by n. Okay, and if you do the computation, you realize that this fellow here is essentially 8, which is the modular ratio, multiplied by AS steel, that I have 4 number 9, so 4 inch squared, plus 1 number 11, that is 1 multiplied by 1.56 inch squared. Okay, so I got this number to be 44.48 inch squared. Okay. All right, in case you're wondering, okay, Bob, you didn't do it here. So this is relatively simple, right? 8 multiplied by AS, 2 number 9 bars, so 2 inch square multiplied by 2 number 8 bars, 7.9 inch squared. Okay, so this number I actually calculate out to be 28.64 inch squared. Okay, 28.64 inch squared. Anyway, so after I get this conversion into concrete, right, I can have my compressive zone here as well. Remember, compressive zone here as well. And since it is negative bending moment, that's why the compressive is at the bottom. My KD just shifted to the bottom, and that is 8.65 inch, 8.65 inch. But be careful, this is not done yet. This is not done yet because I have reinforcement sticking through it as well. I have reinforcement sticking through it as well. Okay, so what is a reinforcement sticking through it? Now let's take a look at the drawings, right? Let's take a look at drawings. So right now, as I see, this is negative 4 number 9s, right? And there's 1 number 11, 1 number 11. So if I want to put 1 number 11 throughout, I might as well just do this, extending out. Okay, extending out here. Okay, and that would be my now 1 number 11 sticking through, right? And there are 2 number 9, 2 number 8. I just need it at the middle span, but you see at the support, they're extending into the support. They're extending into the support. Okay, so how to make that arrangement? So let me play some detailing for you. I say that, look, I just need 2 number 9 here. Okay, 2 number 9 here, and I use another 2 number 8 here extending into the support. Okay, I extended 2 number 8 here into the support. So these details tells me that, these details tell me that these 2 number 8 here, I also need to convert into steel, into steel, Okay, so if I do that, my little extra wings here on the side converted steel equal to N minus 1 AS, N minus 1 AS, and that is 8 minus 1 multiplied by AS. What is this AS here? 2 number 8 bars. So 2 multiplied 7.9 inch squared. All right, so this number here is 11.06 inch squared. 11.06 inch squared. Okay, so this is my section that I need to use to compute my ICR negative. Okay, so now if I call this 1 and this is 2 and this is 3, I can compute my ICR negative. negative, ICR negative. All right. And again, let me quickly skip through this process. And I got this number, and sorry, let me use different color here. And I have gotten this number from my calculation. That is ICR negative 11366 inch to the power of 4. And this is obtained miraculously, right? Without any detail, any process, I just got it. Okay, ICR equal to 11366 inch 4. All right. Okay. So that gives me all the positive and negative moment cross-section properties. Cross-section properties. So how do I use it? How do I use it? Right? How do I use it? So this is how am I going to use it? Okay. So I look at the section. Okay. I look at the section. I say, look, you know, the whole thing here have the middle section and have the end support, right? So let me do the drawing in a simplified manner. This is my column, and that's another column here. And this is my beam here in the middle. All right. And I say that, look, the moment follow this nice diagram here, and this is MA positive, and this is MA negative. Okay. And I want to find out, for example, here, my effective midspan, okay, effective moment inertia at midspan. So how do I do that? How do I do that? So I'm going to use the equation here. I say IE midspan would equal to what? Would equal to MCR divided by MA. Okay, so this is step 3. MCR divided by MA and multiplied by IGT, that is, plus 1 minus MCR divided by MA, bracket outside, to the power of 3, and multiplied by ICR. Okay, now pay attention. This is middle span. All right, that means it is a positive bending moment. That means this is positive. This is also positive. This is also positive. Okay, now I don't know what is my cracking moment, so I'm going to calculate that. So cracking moment equal to FR modulus of rupture multiplied by IG, okay, sorry, IGT, and divided by YT, divided by YT. Okay, now remember this, right? This is the section we're looking at, okay? And this here, Y top, remember, is 7.66 inch, is given, okay? And the total height is also given, which is 24.5 inch, all right? So here, YT, just for information, is 24.5 minus 7.66 inch, okay? So I can plug the numbers, FR, which is 7.5, square root of F prime C, which is 4,000 PSI. Forgive me, I'm a horrible drawing here, okay? 4,000 PSI, and multiplied by IGT, which I just calculated out, which is 33160 inch to the power of 4, divided by this YT here, 24.5 minus 7.66 inch. Okay, so with that, my cracking moment, I got eventually 78 kip foot. 78 kip foot. So that is my cracking moment. That is my cracking moment. Not too bad, right? Not too bad. Okay, pay attention. Again, here we're talking about middle span. We're talking about middle span, all right? So now the MA here should be also positive MA, okay? And that number is given, which is 162 kip foot. 162 kip foot. All right, so immediately I can obtain MCR over MA ratio, that is 75, sorry, clean this up, 75 divided by 162, and I have 0.481, 0.481.
Professor, isn't this
Yes,
78?
oh, 78, you're right. Oh, thank you. Sorry about that. Yes, that's right, 78. Okay. All right, so that is the ratio. Now, one thing I'm still lacking, I have this IGT already. What about ICR? ICR, okay, let me just write it down. Anyway, so IGT plus calculate is 33160 inch to the power 4. ICR, again, this is positive, okay? Positive, all right? So this is 10860 inch to the power 4. How do I get this number? Well, follow the exercise, okay, in last lecture. All right, okay. All right, so this is IGT and ICR, okay? And I can plug in my equation, which is this equation here. So let me rewrite it. IE middle span would equal to, first thing, MCR over MA, that is 0.481. So let me just help you to link it, okay? Help you to link it. All right, that is the equation. So 0.481 is this fellow here, multiplied by a IGT, which is 33160 inch to the power 4, plus 1 minus, okay, 1 minus 0.481 to the power of 3, bracket outside, and multiply ICR positive, okay, ICR positive, which is 10860 inch to the power 4. And add up what you have at the end of the day, middle span, IE, equal to a 13340 inch to the power 4. Okay, so that is my effective moment of inertia at the middle span, at the middle span. All right, such a long process, such a long process. That's why we skipped the detail how to calculate IGT and ICR, okay? But we'll talk about that. We'll talk about that, okay? So,
Question.
yep,
Sorry.
go ahead.
Yesterday, I think in the lecture, the first term in IE mid, the MCR over MA was also raised to the power of 3. I don't know if that
Oh,
wrong.
you're right. You're right. Did I miss that? Yes. Thank you, Kyle. I think I missed it. All right. Yeah, please make a correction. This is power of 3. Okay. And check my number to make sure this number works. I think I have the 3 in the original equation, but just check for me. Okay. Thank you. So again, be careful, okay? We're talking about IE middle span, IE middle span. It is the moment inertia at the middle span. How about the end? How about end? So step number 4, how about 1 and 2? Okay, 1 and 2. So just to maintain consistency, let me just copy this drawing here, okay? Copy this drawing here, and we're going to paste it here. And now, instead of MA positive, okay, MA positive, all right, we're going to look at the end, okay, IE1, and you can name 1 or 2, depends on your preference, okay, but this is how I name my ends. Now, first thing first, right, I know that IE1 got equal to IE2 because it's symmetric, right, symmetric. Symmetric in terms of what? In terms of moment diagram, okay? They're the same moment, but that's why they're the same. That's why they're the same. And they're the same section, of course. Same section, okay? So same section, same reinforcement, okay? Same reinforcement. So 1, 2, 3. 3 reasons make them the same. Okay, so I just have to take a look at 1, and I know the rest of it. I know the rest of it, okay? All right, so supposedly I can use my IGT plus equal to IGT negative to call it good. Okay, so I would say supposedly, right? Supposedly I can use this and go from there to get IGT, isn't it? But I'm sorry, okay, but not really. All right, this is the thing I'm trying to explain you here. Not really. Why is that? Okay, this is special provision by ACI, okay? By ACI. Okay, ACI handle this differently. Handle this differently. Okay, why ACI handle this differently? Let's take a look. Okay, let's take a look. So originally they're the same. Yes, they're symmetric. I mean, they're not symmetric, but they're having the same section, have the same neutral axis. No way they're going to be different. But ACI says because, okay, because when I look at the T-beam, right, and I flip the section because it's negative, right? I flip the section. So let me just put a note here in case you forgot why we do that. Flip the section since it is negative bending moment. It is a negative moment. All right. So when I flipped it, ACI says, look, since you flipped it, I'm going just to take the web. Take the web. Okay, to obtain IGT negative. All right. So I cannot emphasize this enough. This is very, very important. Okay. Very, very important. You say, Bob, you're confusing me. Yes, I am, because this is what ACI says. All right. It's quite different. And because of that, all right, remember this is 14 inches and the total height is 24.5 inch. Okay, so IGT, I'm using red color, okay? You should be careful. IGT negative, right? Negative, only when you have a negative bending moment, okay? That is 1/12 BWH to the power of 3. So in this case, it's 1/12 multiplied by 14 inches and multiplied by 24.5 inch to the power of 3. So your true IGT negative is 17200 inch to the power of 4. Okay. All right. So now I will just put here a not equal sign. So by ACI, it is not equal. Okay. It is not equal. All right. So we have to use this approach. And I want to emphasize again, because you see this in exam, and if you put them equal by mathematics, then we have a problem. Okay. This is engineering. All right. This is engineering. Okay, so get this out of the way. Pretty happy about it, by the way. Then we can look at the real issue here. So first of all, MCR, our MCR negative. Okay, now the MCR negative is no longer the old equation, because now I can use my modulus of rupture multiplied by IGT negative and divided by YT. Okay, YT. Since I'm using this section, okay? Since I'm using this section to calculate my ICR, so everything changes. Everything changes. How? FR, which is modulus rupture, stays the same, okay? Does not change at all. Now IGT would equal to 17200 inch to the 4, okay? Okay, you use that number. All right. Now YT here would equal to half H. All right, half H, okay, which is different from before, right? Different from before. So now FR multiplied by 17, now let me just plug the number, okay? So FR equal to what? 7.5 multiplied by square root of 4,000 PSI multiplied by 17200 inch to the 4 divided by H divided by 2. What is H? 24.5 inch divided by 2. Okay, so just to make it easy, and again, you don't have to wipe it out. You can continue writing. I'm just trying to save space here. This is 12.25 inches. And now my MCR negative, be careful, okay? MCR negative is negative 5.5 kip foot. Okay, where this negative sign coming from, I arbitrarily added to it because I know it is negative. All right, just to remind myself, the applied moment, it is also negative at the end, which is known and is given 225 kip foot. 225 kip foot. Okay, so this is my MCR negative and MA negative. So I do the ratio again, MCR negative divided by MA negative. So I got 55.5 divided by 225. So I got this ratio to be 0.247. 0.247. Okay, such a lengthy process, and I have not done yet. And now I can compute IE1, and that is equal to IE2 using that equation. So this MCR negative divided by MCR negative to the power of 3. And thank you again, reminding me that. And this is IGT negative plus bracket inside 1 minus MCR divided by MA negative 3. So out of the bracket, you have ICR negative. Again, any question? Yeah.
ACR, on the first term there twice.
Did I repeat what?
On the first term there, you have MCR negative over MCR negative.
twice? What do you mean twice? Like
Right after IE2, you have
IE2.
MCR negative over
Oh, you're right. You're right. Yeah, that's thank you. That's typo. You're absolutely right. Thank you. All right. So that is the ratio here. And let me bring the number here 0.247 to the oops. It's a lot of detail today. And to the power of 3 and multiply IGT here and be careful, right? IGT is this fellow here 172. Is it 172.00 inch to the power of 4 plus bracket inside 1 minus 0.247 cube outside ICR. What is ICR cracking? What is it? Sorry. What is this? ICR negative. Where is it at? Let me see. Did I get that number before or not? I think I got this number before somewhere here. Yes, I give this number before, okay? 11366 inch 4. So 11366 inch to the power 4. So I got this final number to be 11450 inch to the power 4. All right. So that, ladies and gentlemen, is my IE1, IE2, and the supports. Okay, IE2, IE1 support. Finally, step number 5. Okay, not done yet. Finally, IE equal to what? We're ready to compute the effective moment of inertia. All right. So to compute this, let me do the drawing again. That is my column, and simplify this in my beam. So IE middle span here, IE mid, I have computed in step number 3, and that is what? Let me see here. That is 13340 inch to the power 4. Now IE2 on the right and IE1 on the left, they're the same. And let me just write this way. And this number equal to what? Equal to this fellow right here, 11450 inch to the power 4. Okay, so with this, now I will say my I effective, use a different equation now, okay? That is equal to 0.5 multiplied I mid, okay? Oops. I E mid span plus 0.25 I E1 plus I E2 bracket outside. All right. So plug the number 0.5 multiply IE mid 13340 inch to the power 4 plus 0.25 multiply 11450 inch to the point of power 4 plus identical. I could have just multiplied by 2, but I want to show you all the details. Okay, so that's what it is. And the final number is 12395 inch to the power 4. And that is, ladies and gentlemen, my moment of inertia for the whole beam. For the whole beam. Okay, such a long, long way and we're done. Such a long, long way, we're done. Okay, all right. Now, let me go back and review quickly here. Okay, so few things. Okay, at the beginning, right? At the beginning, I pull out a negative bending moment, right? Negative bending moment and positive bending moment divided by the regions. And I basically told you already the moment of inertia, IGT, for the positive and negative bending moment to save time because it takes forever to solve. It would take more than 3 hours to get everything done, okay? Don't have that time. But anyway, so I'll give you a shortcut, tell you the number exactly, right? You got the AGT, the ICR for positive bending moment, and you also got IGT and ICR for negative bending moment. With these 4 numbers done, right, what you did is you plug in the IGT, ICR positive to get IE mid, and you get IGT negative and IGT, ICR negative to get IE1, IE2. Then you use I mid and IE1, IE2 to get your effective moment of inertia. Okay, so that is the process. That is the process. Quite a long process, eh? Quite a long process. And now, before I continue, any questions for me on this? Anything, folks? Anything? All quiet? Very boring stuff, eh? Okay, so this is very long, and I presume you will take some time to digest. Please rewatch the recorded lectures and also work through the lecture notes on the stand. I'm gonna leave, if not the last, but one of the few quizzes left. I believe we're on quiz number 9 here, okay? Pay attention, folks. If you're watching this, because you cannot attend, be careful, okay? Quiz number 9. All right, what are the quiz number 9? Now here, again, in this problem, right? In this problem, let me write it out, okay? We ignored the details, okay? Details on calculating IGT positive, ICR positive, IGT negative, ICR negative for the T sections, Okay, so in this quiz, please show details. Okay, I just want you to work through them. All right, so 1, IGT positive, 2, ICR positive, 3, IGT negative, 4, ICR negative. And let me provide you with the section, okay? So the section, T section looks like this. Okay, T section looks like this. Okay, now for the whole thing, right? For the whole thing, and I can provide you the dimension. This is 75 inch. This is 5 inch. The entire height of the section is 24.5 inch. The width is 14 inch. And talk about the reinforcement, right? Reinforcement. These reinforcement, okay, 2 number 8 and 2 number 9, they're at the center of distance right here is 22 inches. Okay, and these are 2 number 8, and these are 2 number 9. Okay, and for the top, I have 4, 2, 3, 4 number 9s and 1 number 11. So 1 number 11 and 4 number 9. Okay, and for the distance here, okay, for the distance here, let me make sure I have a distance here. Sorry, give me 1 second, okay? Let me take a check here. And let's use the distance of, let's try 2.5 inch, 2.5 inch, okay? All right, so this is under the positive, okay? Positive moment, okay? So think about the negative, you just flip it, okay? Think about the negative, you just flip it. All right, so this is quiz 9. All right, okay, any question for me on this? Are we okay on this? Anything? All right. Well, I know few of you want to stay behind and go over their individual exams. Please do stay. If you have any other question, you also are welcome to stay behind or email me. Okay. All right. If not, I'll see you next week. All right. Bye now.
Thank you.
Yeah.
Is
Homework.
there
Yeah.
homework?
Yeah. I will upload the homework right after lecture. You'll see homework 7 tonight. Okay. All right. Let me stop recording and.